Here is example 3 of this problem on page 6 of slides 5-3. So now we suppose a firm has a production function, also called a Cope-Douglas function, given by Q equals to 1.5 K to the power of 0.6, L to the power of 0.4. Assume the budget is 960. And let's put it down here. Budget is 960. And the price of capital equals to 6. And the price of labor equals to 2. Okay, so here, determine the amount of labor and capital that maximizes your output. Okay, so we are to maximize your output by choosing capital and labor. All right. And also estimate the benefit of having an additional dollar in the budget. And here, as we know, the budget is more like a constraint. So the last sentence is basically asks you to report the Lagrangian multiplier at the optimum. Okay, so first, as I emphasized, we need to translate this verbal language into math symbols. Okay, so here, the budget is greater or equal to your total expenditure on recruiting capital and labor. That is the price of capital by capital plus unitary price of labor by total amount of labor recruited. And here we want to maximize, right, the quantity produced. So it's better that we don't leave any money on the table. So here, that's why the equation sign is used rather than the inequality. Okay, and here PK is 6 by K plus PL is 2 multiplied by L. So the result is, so we can kind of simplify this. Let's just do the formal way. So here it is 960 minus 6K minus 2L equal to 0. So this is what do we call the constraint equal to 0. So here, this constraint that we are subject to is 960 equals to 960 minus 6K minus 2L equal to 0. So that is the constraint that we are subject to. So the entire thing above is the problem here defined as an optimal optimization problem. Then we are to solve this problem. It is a constraint optimization because we do have a subject to, right, to follow the objective function. So here Lagrangian is the production function, right? How do you produce Q by inputting capital and labor plus lambda by constraint equal to 0. And here that is 1.5 K to the power of 0.6 L to the power of 0.4 plus lambda 960 minus 6K minus 2L. Okay, so this is the entire thing. Exactly the same as the steps that we take. We first define the problem officially, especially after figuring out what is the constraint, right? Then we just write everything into the Lagrangian equation. Then first order conditions, we have to solve for them. Okay, so 3 things. Partial derivative with respect to K equal to 0. Partial derivative with respect to L equal to 0. Partial derivative with respect to lambda equal to 0, because here the variables are K, L, and lambda. Okay, and then we were to solve. I always start with number 3 because that's easier. That is actually 960 minus 6k minus 2l multiplied by lambda. That is also 960 lambda minus 6 lambda k minus 2 lambda l. Okay, so I'm just writing the lambda product into two forms for preparation of future derivation. Okay, so here for this one, the first term has nothing to do with lambda. The second term, when you're taking the derivative first order with respect to lambda, the result is 960 minus 6k minus 2l equal to 0. Okay, so before doing anything, we can divide 2 to both sides of the equation. So we have 480 minus 3k minus l equal to 0. So here we define this as equation 3. Okay. All right. Now let's look at equation 1. Equation 1 is the derivative, right? 1.5 multiplied by L to the power of 0.4. That has nothing to do with K. So it is 1.5 L to the power of 0.4, K to the power of 0.6. So the first two terms, when you now here are viewing K as the only variable, the first two terms are actually constant multiplied to something including K. Then what is the something including K? That is actually 0.6 to the power of by K to the power of 0.6 minus 1, right? X to the power of alpha, its derivative is, K by X to the power of N, its derivative is K by N X to the power of N minus 1. And here K is 1.5 by L to the power of 0.4, right? N is 0.6, and now X is your K, and N 0.6 minus 1. Okay, that's the derivative first term. For the second term, only this one, minus 6 lambda K is the term including K, and its derivative is just minus 6 lambda. Don't forget the condition, which is equal to 0. So here, then we have 1.5 L to the power of 0.4, 1.5 by 0.6 to the power L to the power of 0.4 by K to the power of minus 0.4 equals to 6 times of lambda. Okay, and that is equation 1. And equation 2, similarly, we have 1.5. Let's just section them. Okay, 1.5 K to the power of 0.6. Now, L is the only variable, right? Its derivative is 0.4 by L, 0.4 minus 1. And therefore, for the second term, the only last one is one that's including L, and its derivative is minus 2 lambda. It's set equal to 0. So what we have is 1.5 by 0.4, okay, K 0.6 L to the power of minus 0.6 equal to 2 times of lambda. That is your equation 2. All right, so we have equation 1 and equation 2 and equation 3. We have 3 equations to solve for 3 unknowns. Looks complicated, but not necessarily the case. Okay, so let's look at them. 1/2. Why is that? Because we have a lot of common term to cancel, right? So the right-hand side is 6 lambda over 3 lambda, which equal to 3. The left-hand side, we have 1.5 over 1.5. That's canceled. And 0.6 over 0.4, we have 6 over 4. Right? Then we have k to the power of minus 0.4 by L to the power of 0.4. That's from the first one. Over k to the power of 0.6 L to the power of minus 0.6. Okay. And here we can further rearrange. So here divide by 2. It's 3/2. Right? 6/4 is 3/2. Right? And also, then we have k to the power of minus 0.4 by k to the power of minus 0.6. Why is that? 1/x to the power of a is x to the power of minus a. So here, that's why we can write this as k to the power of minus 0.6. Similarly, by L to the power of 0.4 by L to the power of minus 0.6, then negative changes into positive. That equals to 3. Don't forget the coefficient 3/2, right? And here, x to the power of a multiplied by x to the power of b equals to x to the power of a plus b. So here we can merge those exponential with the same base. Okay, so we have k to the power of minus 4 minus plus minus 6. Minus 0.4 plus minus 0.6. Multiply by L to the power of 0.4 plus 0.6. Now equal to, here we can flip, right? Here it is 1.5 equal to 3. And this one, 3/2 is 1.5 equal to 3. And then we can divide 1.5 to both sides, and 3/1.5 equals to 2. And here this one is k to the power of minus 1. Minus 0.4 minus 0.6 is minus 1. Multiplied by k to the power of 1. So what is this in the left-hand side? It is actually L/k equal to 2. So that tells you L equals to 2 times of k. Right? We can multiply k to both sides of the equation. Just to make it clearer, so what we have now is L/k equal to 2. That is L equals to 2 times of k. So that is your equation 4, comes from a combination of 1 and 2, and take 4 into 3. So 3 is actually L equal to 480 minus 3k. Okay, then here we can solve for k. So that is 3 and 4. 3 and 4, we have 2k, right? L equals to 2k. So we replace the L from equation 3 with the information in equation 4. So the left-hand side is actually 2k equals to 480 minus 3k. So that's 2k plus 3k equals to 480. 5k equals to 480. K equals to 96. That's K star, which is 480 over 5. Okay, and L star equals to 2 times of K star, which is 2 by 96, 192. So we have K star and L star, and then we just need to take them into equation 1 to calculate for lambda, or equation 2 to calculate for lambda, right? So we have lambda star equal to 0.3 by 96 to the power of 0.6 by 192 to the power of minus 0.6. And this lambda star is how much the benefit is of having an additional dollar in the budget on the total output that you can produce, the optimal output that you can produce with this budget. Okay, so lambda star is benefit of having $1 more in budget on the optimal output Q. That's how we interpret this.